Fine. Let's look at the scalar data representation and also the corresponding isosurface extraction. Also look at the marching cube algorithm. So before we are extracting, let's try to see how data will be represented. Data will be available as samples, where the domain is represented as a mesh. So we have two cases where we have a structured mesh. We have the mesh in terms of a cubic lattice, or you can also have a triangle mesh, which is an unstructured mesh. Uh, and the function values will be specified at the vertices of the mesh. So if we want to know the values within the mesh, you have to interpolate the values, either using linear interpolation or bilinear or trilinear interpolation. Now, let's look at the 2D case, which is how do we extract the isosurface in the 2D case. So let's look at this case where we have where scalar field values. All these points are actually the grid points in 2D. It has values like 9, 7, 6, 5, 7, 4, or all those values. Okay, so once we have these values, we have an ISO value for which we have to extract the surface. So this is the grid representation of what we have. Let's say our ISO value is 5.5. So what we do is there are values in the grid which are actually greater than 5.5 and values which are less than 5.5. We mark all the values which are greater than 5.5, all the vertices which are having values greater than 5.5 as plus, and the vertices which have values less than 5.5 as minus. So we get a representation like this. This is a more simplified representation for ISO value extraction. Now what we do is we know that the ISO points are going to lie. It's not going to lie on every grid. It is going to lie between wherever there is a change between a plus and a minus. So all these vertices, edges which join two vertices which have a change between a plus and a minus, the ISO lines is going to lie between them. First is we have to identify the ISO point. So we do an approximation where we wherever there's a change between a plus and minus, wherever there's an edge which has a change, we mark their midpoints as the corresponding ISO points, which is kind of an approximation, not exactly. So in a case here also we'll looking at 5.5 anyway. Okay. Now we have marked all the ISO points. Now we have to generate a contour out of it. So we have to join these ISO points. How do we join these ISO points is the next question. So for joining the ISO points, we use a linear linear connection where we join it by piecewise linear functions. So we just join them like by those points by line segment. Okay. But so what marching cubes actually does is marching cubes is you don't have to look at the global isosurface extraction or the global contour, but you have to just go through each grid or each cell and look at how the vertices have values are actually vertices scalar values are actually oriented or distributed and obtain join the isopoints for those vertices in some specific fashion. So this will lead to, so if you have a 2D column, so 2D grid. So we have, let's look at a single cell. This is a single grid of the of this big larger picture. This is like all these grids we have together. So this each vertex can have two values, right? So the entire vertex can have 2 raised to 4, which is 16. So there are 16 different cases in which the plus and minus signal, plus and minus values can be distributed across the vertices. So these are basic permutations. There are 16 permutations, but we'll only consider 4 cases because the other cases are actually symmetrical. For example, there's a case where there's 1 plus and all the 3 are minuses. So we can get 4 similar cases where the plus is on the next vertex vertex, the plus is here. All these are rotational cases of this particular grid. So all these are grouped together. There is another case where I have two pluses and two minus, where two pluses are actually adjacent and two minuses are adjacent. Also, there's a case where we have uh, one minus and three pluses in the corresponding vertices. And there are cases where pluses are and minuses are in the diametrically opposite vertices. So these are the cases. And how do we connect these isopoints? This is like a case table which we use for this. So in a plus case, this is how we connect. One plus and all three other vertices are minus. This is how we connect it. This is how we connect the isopoints. So here we have two isopoints. In the second case also, you have two isopoints. So the paths which are actually slashed or marked with slashes are actually considered to be inside the iso contour. Um, Fine. So this is how we mark. So on the first three cases, we have two isopoints. But there's a case where you have four isopoints, where you have pluses and minuses on diametrically opposite directions. So in that case, you can actually join isopoints in two different ways. This is one way of joining them, and you can also join it using the other way. So how do you join them actually leads to some kind of an ambiguity, which we'll discuss later after we discuss the marching cube algorithm. So the marching cube algorithm is actually a 3D uh, extension of this. So here we had 2D grids, and instead of that, you have 3D voxels, which you're looking into. You will be moving into each cube will be considered at a time, and you will be finding the isosurface for that. So marching cube algorithm, there's a cell-wise construction of the isosurface, and you use bilinear interpolation to find the values. The blue values are actually in the interior, and the red values are in the exterior of the isosurface. Similar to the previous case, here we have 256 cases, but after considering symmetry and all, you have about, I think, how many are there? 16, I think 16 cases, or no, 15 cases. 15 cases are there, and using these tables and based on the configuration of how the plus and minus signs are distributed, we obtain the isosurfaces. So let's look at some cases. For example, this is where we have one plus here and all are minuses. So we have three iso points, and this will be joined by a triangle. There are other cases where we have two pluses and all other minus. Then we have four iso points. There could be cases where we have six iso points, and if it's a four iso points, then we have a quad. And if it's then this quad can be again divided into two triangles. Similarly, if you have six iso points, we'll get something like a hexagon, and we can divide it into four triangles. So these are the multiple cases. There could be also cases where the shapes are not planar or shapes are separated. Like the cases where here we have something like a bent hexagon. Sorry, it's not a hexagon. 1, 2, 3, 4, 5, 6. Bend, yeah, hexagon. So here we have two separate quads which are separated by some distance, parallel quads, parallel triangles. All these cases are possible. Okay, so this is how we have isosurface extraction using the marching cube algorithm. Let's end the discussion here.